Welcome everyone to today's lab on systems programming. Today we are going to learn about file systems, how files are stored, how the operating system manages them, and how your programs actually interact with this file system. This is one of the fundamental topics in systems programming, so let's get right into it. Here's our roadmap for today. We'll start with the big picture. What is a file system and why do we need one? Then we'll look at two core abstractions, files and directories. After that, we'll go through the system interface, the actual functions your program's called to interact with files. Then we'll build up a very simple file system from scratch, walk through read and write operations step by step, and finish with how caching and write buffering makes all of this faster in practice. Let's start with the big picture. One of Unix's defining design principles is that everything is a file. Network sockets, hardware devices, data on disk, they're all accessed through the same file interface. This is a really powerful abstraction because it means the same set of operations can be used to interact with very different things. Now, a file system is a specific implementation of this file interface. It decides how data is actually organized and stored on the disk. Different file systems make different trade-offs around performance, scalability, and how they handle failures. If you look at the diagram on the right, you can see this layered architecture. Your application sits at the top in the user space. When it makes a file operation, it goes through a system call into the virtual file system layer, which is the key abstraction that lets systems support multiple file system types at once. Below that sits the actual file system implementation, and at the bottom is your SSD or your hard drive. Some popular examples include ext4, NTFS, and FAT32. procfs and sysfs are virtual file systems that expose kernel and process information as file, whereas tempfs stores files in memory. Now, let's look at the first core abstraction, the file. At a high level, a file is just a linear array of bytes. That's it. The file system doesn't care what's inside, whether it's text, an image, or a binary. It just sees bytes. Each file has a low-level identifier called the inode number. This is how the file system actually refers to files internally, not by name, but by this number. The inode is a data structure that stores two things. First is the metadata about the file, its type, whether it's a regular file, a directory, or a symbolic link, its size in bytes, the permissions of who can read, write, or execute it, its owner and its group, and finally three timestamps about when it was created, last modified, and last accessed. Second, the inode contains pointers to actual data blocks on disk. You can see this in the diagram. The direct pointers point straight to data blocks. For small files, this is all you need, but for larger files, you need indirect pointers. An indirect pointer points to a pointer block, which then points to the actual data blocks. This gives you an extra level of indirection that lets you address much more data. To access file metadata, you use the stat system call, whereas to create a file, you use open. The second core abstraction is the directory. A directory also has an inode number just like a file, but its contents are specific. A directory stores a mapping between human readable names and inode numbers. So when you see a file called foo in a directory, what's actually stored is the pair, the name foo and its inode number, say 10. Directories form a hierarchy. At the top is the root directory, which is just a forward slash. The forward slash is also used as a separator between directory names and file names in a path. So when you look at this example, you're saying start at root, go into the foo directory, then into bar, and then find hello.txt. Now, let's talk about the interface, the operations you can actually perform on a file system. At the highest level, there are three categories. You can create files or directories, you can access them, meaning read from them or write to them, and you can delete them. We'll now go through specific system calls for each of these. But before we dive into system calls, let me show you a really useful tool, strace. Strace traces all systems calls that a program makes. It's incredibly helpful for debugging and understanding what's actually happening under the hood. Here in this example, as shown, I am running strace on the command cat foo. Let's walk through what happens. First, open AT opens the file foo in read-only mode and returns file descriptor 3. Then fstat gets the file's metadata. The fadvice call is nothing but just a hint to the kernel that we'll be reading sequentially. Then mmap allocates a read buffer into memory. Now the actual IO happens. Read pulls from 6 bytes from the file descriptor 3, that's the contents hello followed by a new line. Then writes sends those same 6 bytes to file descriptor 1, which is std out, which is basically your terminal. Finally, another read returns nothing. We have hit the end of the file. So even a simple command like cat involves multiple system calls, and strace lets you see every single one of them. Now, let's look at how files are actually opened and managed. The open system call takes a path name, flags that specify how you want to open the file, and a mode for permissions if you are creating a new file. It returns a file descriptor, an integer. A file descriptor is not a global thing. Each process has its own set of file descriptor. Looking at the diagram, you can see the three-level mapping. On the left is the per process file descriptor table. File descriptor 0 is always standard input, 1 is standard output, and 2 is standard error. When you open a file, you get the next available number. Here fd3 points to file A and fd4 points to file B. The FT table entries point into the system-wide open file table. This is shared across all processes. Each entry here tracks the current offset into the file, where the next read or write will happen, the flags the file was opened with, and a reference count. Finally, each open file table entry points to the actual inode of the file. The inode is what we just talked about. It has the metadata and the pointers to the data blocks. This three-level architecture is important because it means two processes can open the same file independently and each have their own offset. Or a process can have multiple file descriptors pointing to different positions in the same file. Here are the four core operations you will mostly use. Read takes a file descriptor, a buffer to read into, and a count of how many bytes you want. It returns the number of bytes actually read. Write is very similar in the sense that it takes a file descriptor, a buffer containing the data you want to write, and a count. It returns the number of bytes actually written. Lseek lets you change the read or write offset into the file. Remember that the OS tracks this offset in the open file table for each open file. And finally, close releases the file descriptor. This is important because if you forget to close files, you'll eventually run out of file descriptors, which is a common bug in long running processes. There are several other important operations for files. Start retrieves the metadata we talked about, which is size, permissions, timestamps. Rename changes a file's name, and unlink removes the file. However, unlink doesn't necessarily delete the file's data, it removes the directory entry. The data is only freed when the link count drops to 0. For directories, mkdir creates a new directory, readdir reads the contents of a directory, and rmdir removes an empty directory. And then there's fsync, which is important for persistence. When you call write, the data doesn't necessarily go to the disk immediately. It might just sit in a buffer in memory. Fsync forces all buffered writes for a file descriptor to be flushed to the disk. This is critical for applications like databases that need to guarantee data is actually persistent. Now, let's talk about links. There are two types. A hard link, which is created with the ln command, gives an existing file a second name. Looking at the diagram, both foo and bar are directory entries that point to the same inode, which is inode 10. The inode's link count is 2. The file's data is only deleted when this link count actually drops to 0, meaning all names for the file have been removed. One limitation is that you cannot hard link across disk partitions because inodes are local to a file system. And you can't hard link to directories that would only create cycles in the directory tree. A soft link, on the other hand, or a symbolic link created with ln-s is different. It's actually a separate file with its own inode, which as you can see is inode 20 in the diagram. The data stored in that inode is just the path to the target file. When the OS encounters a symlink, it reads the stored path and resolves it to find the actual target. The important consequence, however, is that soft links can dangle. So if you delete the target file, the symlink still exits but points to nothing. You will get an error if you try to follow it. Two more operations we would want to understand is mkfs and mount. MKFS writes an empty file system onto a partition. You give it a device and a file system type. For instance, this command creates a fresh ext4 file system on the first partition of your disk. This sets up the superblock, the bitmaps, the inode table, all the on-disk structures the file system needs. Mount is how you make a file system accessible. It attaches a file system to an existing directory in the directory tree called the mount point. For example, this command takes the file system that we created and makes it appear under /mnt. As you can see in the diagram, after mounting the files from the external device, which is file1.txt and file2.txt, appear as children of /mnt in the directory tree. From the user's perspective, they look like any other files on the system. Now let's move on to build a very simple file system from scratch to really understand how things work at the disk level. We're going to keep things minimal. Our disk will have 8 blocks, each 4 kilobytes in size. Inodes are 256 bytes, so we can fit 16 inodes in a single block. Looking at the block layout, block 0 is the super block. It contains metadata about the file system itself. The OS reads this first when it's mounting. Block 1 is the inode bitmap. It tracks which inodes are free and which are in use. Block 2 is the data bitmap, same idea but for data blocks. Block 3 is the inode block. It holds all 16 of our inodes, and blocks 4 through 7 are 4 data blocks where actual file and directory contents are stored. This is obviously a tiny file system, but it has all the same components as a real one, like ext4, just scaled way down so we can trace through operations by hand. Now, let's look at how we find a specific inode on disk. We said 16 inodes fit in one 4 kilobyte block, because each inode is 256 bytes and 4096 divided by 256 is 16. To locate inode n, we use two formulas. First, which block is it in? So block equals inode start plus n divided by inodes per block. Second, what's the offset within that block? N modulo inodes per block times 256 bytes. Let me give you a concrete example so that it makes sense. Say we want inode 12, it's in our inode block, which is block 3. The offset is 12 times 256, which is 3072 bytes into that block. You can see this in the diagram. Inode 12 is highlighted, sitting at offset 3072 within the block. Now, let's see what a directory looks like in a simple file system. Directory is just an inode whose type field is set to directory. It works exactly like a regular file. The inode has pointers to data blocks. The difference is what's stored in those data blocks. Looking at the diagram, inode 2 is our root directory. Its type is directory, its size is 4096 bytes, and its first pointer points to data block 4. If we look at the contents of data block 4, we see a table, a mapping of names to inode numbers. There are 4 entries. Dot refers to the directory itself, inode 2. Dot dot refers to the parent directory, also inode 2 in this case, since it's the root. Then foo maps to inode 12 and bar maps to inode 13. This is exactly how the file system resolves path names. It reads these tables to translate names into inode numbers, one directory at a time. Now, how does the file system know which inodes and data blocks are available? It uses bitmaps. A bitmaps is simply a sequence of bits where each bit corresponds to one inode or one data block. A 1 means it's in use, a 0 means it's free. Looking at this inode bitmap, the first 4 bits are set to 1. Inodes 0 through 3 are in use. The rest are all zeros, meaning inodes 4 through 15 are free. The data bitmap has 4 entries since we only have 4 data blocks. The first 2 are set, data block 0 and 1 are in use, and the last 2 are free. When the file system needs to allocate a new inode or data block, it scans the appropriate bitmap for the first 0 bit, sets it to 1, and uses that slot. When a file is deleted, the corresponding bits are set back to 0. Now, let's trace through an actual read operation step by step. We're going to open the file /foo/bar and read its contents. The file is 8 kilobytes, which means it occupies 2 data blocks. The file system has to traverse the directory tree to find the file before it can read any data. Let's see exactly what disk operation that requires. Here's every single disk IO that happens. Let's walk through them one by one, and I'll highlight the corresponding block on the disk layout as we go. The open phase starts. Step 1. We read the root inode to get the root directory's data block pointer. Then we read the root directory's data block and look up the name foo. We find it maps to inode 12. After that, we read inode 12, which is the foo directory, to get its data block pointer. Step 4 is that we read foo's data block and look up bar. We find it maps to inode 13. Step 5 is that we read inode 13, which is our target file. Now we have all the information we need, and the OS returns a file descriptor. That's just 5 reads just to open the file, and we haven't read any actual data yet. Now the first read call, step 6, we read the bar inode again to get the address of data block 0. Then we read the bar's data block 0, that's the first 4 kilobytes of file data, after which we write back to the bar inode to update the last access timestamp. The second read is the same pattern. Read the bar inode for data block 1's address, then read bars data block 1, followed by write the inode again for time stamp. So reading an 8 kilobyte file required 11 disks IOs, 9 reads and 2 writes, and that's for a file that's only 2 directories deep. You can only imagine how this adds up for deeply nested paths. Now let's look at a write operation. This time we are going to create a new file at /foo/bar and write 4 kilobytes to it. That's one data block. Writing is more expensive than reading because we need to allocate new inodes and data blocks and update the parent directory. Let's trace through every IO like we did before with read. The create phase starts again, and steps 1 through 4 are the same as before. You read the root inode, you read the root data to find foo, you read foo's inode, and then you read foo's data. But in step 4, instead of finding bar, we are checking that it doesn't already exist. Now we need to allocate an inode for the new file, which is step 5, where you read the inode bitmap to find a free slot, followed by writing the inode bitmap to mark that the slot has been allocated. And then you also write the new bar inode to initialize it with the file type, size, and other metadata. Then we update the file directory, which is step 8, where we read foo's data block to prepare for the update. After that, we write foo's data block to add the new entry, the name bar and its inode number, followed by writing the foo's inode to update its metadata. The directory size changed and the modification time also needs to be updated. That's just 10 IOs to create the file. Now the actual write follows, which is step 11, where you read the data bitmap to find a free data block, followed by writing the data bitmap to mark it as allocated, and then you write the actual file data to the data block, and lastly, you write the bars inode to update the file size, add the data block pointer, and set the modification time. So in total, that was 14 disk IOs, which has 6 reads and 8 writes for creating a file and writing 4 kilobytes. Compare that to the 11 IOs for reading. Writes are, as you see, significantly more expensive because of all the metadata updates and allocations involved. So 14 disk IOs for a single write is obviously not great, which is why caching is essential. Read caching is straightforward. The OS keeps recently read blocks in memory in what's called the page cache. So if we read the root inode once, the next time we need it, it's already in memory. No disk access needed. The OS uses LRU, which is least recently used, as the eviction policy to decide what to throw out when the cache is full. Write buffering goes further. Instead of writing to disk immediately, the OS buffers writes in memory. This has three big advantages. First, you can batch multiple updates together into a single disk write. Second, you can schedule IO better, which is sequential writes are always much faster than random writes, especially on spinning disks. And third, you can sometimes avoid writes entirely. If a file is created and deleted before the buffer is flushed, the data never needs to hit disk at all. But there's a trade-off. If the system crashes before buffered writes are flushed to disk, that data is lost. This is exactly why fsync exists. It forces the OS to flush all pending writes for a file to disk. Databases uses fsync extensively to guarantee durability. And modern operating systems use what's called a unified page cache. The same cache is used for both virtual memory pages and file system data, which makes very efficient use of available RAM. And that wraps up our discussion of file IO. We have covered the file system abstractions, the system call interface, walked through how a simple file system handles reads and writes at the disk level, and seen how caching makes it all practical. So thank you all for listening. I will see you in the Q&A session where we can discuss any questions you have about today's material.